we're going to take the next step now. We're going to look at what happens when we take when we're interested in a numerical variable like weight, blood pressure, age, blood sugar levels. You can name a million of them, right? So we're going to take a look at when we sample a population for things like numbers, for things that we would express in numbers, numerical variables. We know that we're not going to get an exact picture of what that population is from a sample, but the sample should at least give us an idea. It should mimic what the population looks like. But there's a lot of chance involved. We may get a lot of people that are lower than the average person in the population, or higher than the average person in the population. So we have to start to think about, when we take a sample, how does our sampling methodology, how is that affected by chance? What role does luck play in our sample being an accurate reflection of that population? Are you guys okay with that? Any questions so far? I've been pretty much talking in general terms here so far, so probably not too many questions. But if you do have one, type into the chat box so I can address it, so that we don't fall behind on this. Okay, so I am going to take a look at the material that we have in session 4 for today, and we have 2 areas here. One area is we have a lecture that Levi Waldron did. Actually, it's not a lecture entirely. It's sections of a lecture, right? So we have a couple of parts of this lecture. And I have it all in one. I have another version of this where I have it broken up into smaller bits. I'm wondering, we can see it as a single lecture. It doesn't really matter. But what I'm going to do first is I'm going to take a look at our own laboratory version of this. I'm going to do a little bit of a hands-on work with this. Okay, so what I'm going to do now is I'm going to pull up a sheet of paper here that I can write with. And I'm going to get that out of the way. I've got 2 copies of that open. Okay. Okay, so whoops, that went away. Okay, there we go. All right. Okay, so I'm gonna take a look at a numerical variable, something like, let's say, I'm gonna take a look at a variable that's called blood pressure. Okay, so now if I sample a population, here's a population, right? Let's say that there is 1 million people in this population. Right? Now those 1 million people, each one of them has a specific blood pressure. Maybe maybe we could screen them for it. Maybe they've been tested, so on and so forth, but they have a specific blood pressure. So I don't have the resources to sample everybody in the population. What I really want to know, what I'd really like to know about this population is what the mean of the population is, what the middle is, and what the standard deviation is. Now notice I'm using Greek letters for this. When I use Greek letters, I'm referring to something called parameters. And parameters are values related to the entire population. When I look at those same values, when I'm looking at where a sample is concerned, I'll use the term X bar for the mean and SD for standard deviation. I'll reserve these symbols for when I'm talking about population and the mean. So let's say that the population and mean average blood pressure for this population is 100. Okay, now that tells us where the middle is, right? So it gives us an idea that on the average, blood pressure of individuals in this population, 1 million individual in its population is 100. Some of them are less than 100, some of them are more, but the average is 100. The standard deviation gives us a window on the level of variability. How spread out are the blood pressure readings? So I'm going to say that the standard deviation for blood pressure readings is 10. Okay, now I think millimeters of mercury, I think, is probably what we're using as units here, but I'm not going to worry about the units at all. Okay, so now these parameters are things that I may never know. Certainly, I'll never know the mean. Why will I never know the mean? Well, I'll never know the mean because I'll never have the resources to test all 1 million people, right? Or the desire to necessarily test all 1 million people. So that mean, that mu, is always going to be unknown to us for the most part. There's only one place where it isn't unknown. Can anybody tell me on Blackboard, where's the one spot where I can actually calculate, I can actually see values that represent the mean of an entire population? Any opinions on that? I think you guys got something in the mail in the last month or two, right? A lot of controversy over it in the newspapers as well, because they're actually going to add they're thinking of adding a question to it about citizenship. Got an opinion there? It's a census, right? Census is an actual count. In fact, it's in the Constitution that the census cannot be statistically derived. We can't just, sample some people here in this part of the country, Northeast, Southwest, so on and so forth, in each state or something like that. We can't just sample them and predict what the nature of the populations is in each of the states based on the sample. Although as statisticians, we would love to give that a try. But we're not allowed to do that. The Constitution says it has to be an actual count of the people in the country, right? So that's one of the few places where we're going to actually have an opportunity to perhaps okay, I should be back now. Okay, that's one opportunity that we actually have an opportunity to see the means of populations, like for instance, family size, income, so on and so forth, because everybody is responding to that. Okay, or whatever the questions are. Be honest with you, I don't remember what the questions are off the top of my head. So in statistics, in public health, we rarely have an opportunity to measure an entire population. So a lot of our work has to be done based on what we know about a population from samples that we take from that population. So the first thing that's very important is that whatever we're doing, our sample has to be independent and it has to be random. If it's at all biased in some way, if we're oversampling certain parts of the population in preference to others, then our sample results are not reliable anymore. So assuming that our sample is truly random, so that we're really getting a picture of what this population looks like, right? We want to know how can we estimate what the mean and the standard deviation of this population is. Well, okay, so if I start taking random samples from this population, let's say that I take a random sample of size 10. Okay, well, each one of these people is going to have a blood pressure. It might be 90, 105, 99, 102, so on and so forth. So I'll wind up with 10 numbers that represent my sample. They've been selected randomly, maybe a phone survey, maybe just doctors going randomly to houses or something like that. Whatever we need to do to get a random sample, right? Well, first thing I can do here is I can get a picture of what this looks like by taking the average of these numbers. So let's say that X bar is equal to 98. Well, the true mean is 100, but we don't know that, do we? Right? All we know is what we got from our sample. So our sample, if I take a sample of 10 people, I might get 98. If I took a sample again of 10 people, I might get 103. If I took a sample again, I might get 100. I might get lucky and actually get it right, perfectly right. Okay, so there's a certain amount of variability, a certain amount of chance here. Well, what do you think one of the things that we can do is that we can do to reduce the likelihood that we would be very far from the true population mean when we take a sample? Anyone who want to hazard a guess? Sometimes I'm not going to have time to like really wait for you to type in a comment, but it's going to be sample size, right? Sample size is an obvious way for us to get a better picture of what the population is like from our sample. Whoops, go back. Okay, so sample size is going to have a big impact on this. The larger the sample size is, the more reliable is our picture of what that mean is. So the two things we're really interested in here are the middle. Where's the middle of this population? What's the average, right? In other words, the mean or the average, the middle of the population. We could also use median. Typically, mean is used a bit more. You'll see why in a moment, because mean has a special relationship to the standard deviation, right? Remember how we had to calculate it using, we had to calculate the standard deviation based on the mean and the differences between each individual value. So we're interested in the mean, and we're also interested in the spread, how spread out this is. Okay, and in that case, we're interested in the standard deviation. Right, so those two numbers are going to tell us a lot about the distribution of values for blood pressure in this population. Okay, so I am going to turn this off, and I'm going to pull up a fresh sheet of paper. And I'm going to plot a distribution. You may remember that if I took a sample as I did before, I could draw a histogram. Right? Let's say this histogram represented, this box over here represented blood pressure of 80 to 85, and this represented 85 to 90, and this represented 90 to 95, 95 to 100, 100 to 105, and so on and so forth. You know that in this case, if I were going to look at a sample from this population, I would expect the most values to be near that middle, near 100. So the frequency, the number of times I would expect to find people that are in that range of, say, 95 to 100, 100 to 105, I would expect a fairly high frequency. And then as I got further away from that, higher or lower, I would expect to find fewer people that had that blood pressure. And further away from that again, fewer people that have that blood pressure. Until we get down to blood pressures, say the blood pressure before 80, below 80, well, that sounds, like it's going to, like the higher blood pressure diastolic, yes, the higher blood pressure. If you were considering that, that would be relatively unusual to find somebody that's that low. And it might be relatively unusual to find someone with a blood pressure of 160, for instance, right? That would be a bit concerning. So you would see relatively few people, smaller peaks in our histogram. Well, if I take these, now I made big bins here. I made bins that were, say, 100 to 105. If I made these bins narrower and narrower, these bars would get narrower and narrower to the point where if I have a really large population and I plot all 1 million people in very narrow bars, it's going to start to look like a continuous curve. Like that. In this case, what we're seeing, this continuous curve, is telling us that the middle of the curve is here, and it's bell-shaped because the probability of finding someone randomly that's below that or above that is just based on chance. This is a normal distribution. This is a distribution where whether a person is a person you would pick out randomly is above or below the mean, just based simply on pure chance. The other nature of this is that this is symmetrical. In other words, the mean and the median are in the same point. So 50% of the people are above the mean, 50% of the people are below the mean. So the mean and the median are the same. Also, they are symmetrical. In other words, they have a mirror image shape on both sides of the mean. Okay, that's that's what we would call a normal distribution. Okay, now not every distribution is normal. So for instance, you might have some distributions that are skewed. So let's say an income distribution, right? This might be the income distribution for the United States. You have a middle class here, right? Here's the mean salary for people that are in the, say, the middle class and so on and so forth. But you have a small number of people that are extremely wealthy that may have very, very high incomes, right? And you have some people that have very low incomes, but the difference between the mean for middle class, the average mean might be $50,000, and poverty down here might be $10,000. But the difference between the mean and the highest earners could be millions of dollars. I'd say $50 million. I think Jeff Bezos' salary was this year. Right? It could be very large. So what happens is that this distribution does not look normal. It's not symmetrical. And these people here actually pull, the median might be here, but what happens is what the median and the mean are separated, right? Because this average pulls the mean to the right. These very large values has very little effect on the median because there's very few people here. So the median's only going to be, if there's 50 people up in this area over here out of this million, then those 50 people are only going to pull the median over 50 people. So it's maybe instead of 50K, it'll be 50,100 or something like that. But the mean can be drastically affected by that because it's an average. When you have very high numbers, that average can really pull the mean over to the right. So this specific distribution is positively or right skewed. Okay, it's a skewed distribution. It's skewed to the right by these values. So if you want to remember whether or not it's positively or right skewed, just remember that if it pulls the average up, right, it pulls the average up away from the median, that means it's right skewed. We could also have distributions. How about weights of babies, where you have normal sized babies, and then you have premature births that are very low birth weight, right? That is left skewed or negatively skewed. You can also have distributions that have other kinds of properties. So for instance, maybe a distribution where you have one peak and you have a second peak, right? What do you think that might be? Where might you see something like a skewed distribution which has two peaks, and each one of those peaks would be called a mode, right? Each one of those are the most frequent values, right? So be a mode. So where might we see a situation where we have something that's a bimodal, has two modes like that? Anybody want to hazard a guess? Well, I can't get you guys to stick your necks out here. You're going to get penalized for guessing. Anybody want to hazard a guess? Well, how about if I told you that this represents the heights of students in Hunter Heights, right? This is the heights. Well, why would they be bimodal, right? Well, if you combine the females and the males into one single distribution, chances are the females are going to have one mode, one frequent, one average or mode, and the males are going to have a different one that's just going to be bigger. So it would not be surprising to see this kind of distribution when you're looking at all of the plot of the histogram or plot of all of the values for height for males and females together. On the other hand, you might see something that would, if you look at them individually, it might be normal. But if you put them together, right, because this one is skewed over to here, then put them together and you might see a bimodal distribution. Okay, you guys okay with this so far? And I keep saying that because I want to make sure that I don't lose you guys somewhere along the way. I know it's not that complicated, but it's easy to kind of get off track here. Okay, good. So let's Let's take another look at this now. The reason why we're so interested in these values, mean and standard deviation, is because there's a special relationship between these values when you consider a normal distribution. Okay, and I'm gonna show you that relationship right now. So I'm gonna draw a normal distribution. I'm gonna say that this is, let's see, this is, I'm gonna use blood pressure again. Why not? And I'm gonna say the average is 100. So that's mu. And I'm gonna say the standard deviation is equal to 10. So what am I talking about here? Am I talking about a population or a sample? Anybody want to give me a little input on that? Is this a population or a sample that I'm describing? It's a population, right? Because I'm using the Greek letters mu and sigma. Okay, so let's take a look at this. One of the things that we know about normal distributions is that the standard deviation describes the spread or the distribution of these values inside this distribution. Okay, and so I can tell you, for instance, that we have a rule, a general formula or a rule called the empirical rule, or the empirical formula. Okay, this is an estimation. It's not 100% accurate, but it's true for any normal distribution. It's basically true for any normal distribution. If you go one standard deviation below the mean and one standard deviation above the mean, you have approximately 68% of the population between those two values. Okay, so what would that be in this case? What would those two values would that be? That's one standard deviation below the mean to one standard deviation above the mean, right? Well, standard deviation is equal to 10. The mean is 100, so we're talking about 90 here, and we're talking about 110 here. So 68% of that population is between 90 and 110. That gives us an immense amount of information. If we know that, if we know the mean and the standard deviation, we now know a lot about the way that these values are distributed. Okay, so let me ask you this. If I asked you what percentage of the population was between 90 and 100, what would you tell me? Okay, well, remember what I mentioned about the normal distribution being symmetrical? Well, if this is 68%, well, the area to the left of the mean, one standard deviation, is going to be 34%. I'm rounding these off a little bit. We got them even a little bit more accurately. And for the mean above is going to be 34% as well. Okay, so that gives us a bit more information as well. Now, let me ask you again, what percentage of this population is going to have a blood pressure below 90? Anybody want to hazard a guess? Well, we've accounted for 68% here, right? That leaves 32% of this population. Okay, so if we have 32% of this population left, again, we have this area unaccounted for, we have this area unaccounted for. So since it's symmetrical, these areas are the same. So 16% of the population would be here, and 16% of the population would be here. Again, a great tool, because if we wanted to only treat the highest 16% of the population for elevated blood pressure, well, now we know what our cutoff point has to be for that blood pressure. We start treating at that level, right? Or maybe if I wanted to know like 95%, and I only want to treat the top 5%, well, I can't get that from here yet, but maybe I can get a little bit closer. So let me put this away now. Let me take this another step. Okay, so here's our normal distribution again. Okay, here's our mean, which is 100. Our standard deviation, which is 10. I'll call this blood pressure. Okay, so now let's go two standard deviations to the left and to the right. Now with two standard deviations to the left and the right of the mean, Okay, so this is -2 standard deviations and +2 standard deviations. So what are these values? -2 standard deviations. Standard deviation is 10. So this is 20 below the mean, 2 standard deviations. So this would be 80, and this would be 120. Okay, well, in this case, the area to the left, the area between these two values is approximately 95% of this distribution. So that means that 95% of the people in this population would have a blood pressure in the range of 80 to 120. Okay, handy rule, this empirical rule. So if I were to ask you what percentage of the population has a blood pressure below 80, right? In other words, this area in here. What is that area now? Well, that area is going to be, even though it doesn't look like it because I didn't draw it that well, that area is going to be the same as this area over here. So what area of the population does that represent? Well, there's 5% of the population unaccounted for here. So this is going to be 2.5%. And this is going to be 2.5%. Right? So if I were to ask you what percentage of the population has a blood pressure above 120, you would be able to tell me based on the standard deviation and the mean, you'd be able to tell me 2.5% is above that. Well, okay, that sounds pretty good, right? So now that's pretty handy, just so we know. And again, I'm going to repeat that. One standard deviation to the left and right was 68%. Two standard deviations to the left and right, 95%. And three standard deviations to the left and right captures almost the entire population. That is equivalent to 99.7%. I think 99.3, 99.7, not close enough. 99.7, I think it's close enough. Okay, okay, there you go, 2.5. Thank you very much for the response. Okay, so three standard deviations in either direction is equal to 99.7% of the population. Okay, so we don't always know what the population is like, but if we do, we don't always know what mu is, we don't always know what sigma is, but when we do know that, this gives us we have a big benefit from knowing this.